Hi everyone, this is Tanishk AP211101026 and welcome to this brief introduction to SLR parsing. Today we'll be exploring the fundamentals of SLR parsing, a technique used in compiler design to analyze the syntax of a programming language. Let's dive in. At its core, SLR stands for Simple LR and SLR parsing is a bottom-up parsing technique. Parsing is the process of analyzing a sequence of symbols to determine its grammatical structure according to a given formal grammar, often represented by a context-free grammar. Before we delve into SLR parsing, let's briefly understand LR parsing. LR parsers are a class of bottom-up parsers that read input from left to right and build a rightmost derivation tree in reverse. LR parsers are a powerful and can handle a wide range of grammars, making them popular in compiler constructions. However, LR parsers face a challenge known as conflicts, which occur when a parser is unsure about the correct action to take. Conflicts can lead to ambiguity and hinder the parsing process. This is why SLR parsing comes to play. SLR parsings are a specific type of LR parsers that addresses some of the conflicts encountered in the general LR parsing. SLR stands for Simple LR, emphasizing its simplicity compared to the other LR parsing techniques. There are some key characteristics of SLR parsing. SLR parsing generally has lookahead symbols, which reduces the complexity compared to more advanced LR parsers. It maintains a parsing table that maps the current state and look ahead symbols to next action, which can be shift, reduce, or accept. Also, it has a reduced number of conflicts as by carefully selecting the items in the canonical sets. SLR parser minimizes conflicts, making it simpler and far more efficient. Now let's consider some practical applications. SLR parsing is widely used in compiler construction to analyze and validate the syntax of programming languages. Its efficiency makes it a popular choice for many compilers, contributing to the successful compilation of source codes. SLR parsing is valuable in compiler design. Its simplicity and efficiency make it practical choice for most of the applications. While it may not handle all the grammars, understanding SLR parsing provides a solid foundation for exploring more advanced parsing techniques in the broader field of compiler construction. A crucial component of SLR parsing is parsing table. This table, which I earlier discussed, guides the parsing process by mapping the current state and the lookahead symbols to the next action. There are three possible actions: shift, reduce, or accept, as I discussed. And the parsing table essentially encapsulates the decision making process of the parser. All this will be shown ahead in the video. Let's briefly outline the steps of SLR parsing. Canonical items, beginning with LR0 items that represents the potential states of LR parser. These items can capture viable prefixes and help in decision making during the parsing. There are closure operations which performs various operations to find all the different items that can be reached for from the final LR0 items. These steps help to identify the possible transitions between the states. There are go-to operations to determine the transition between the states. This operation is crucial for building LR0 sets, that is canonical LR sets, and establishing the parsing table. And building a parsing table, with just as said, it associates each state and lookup symbol with the appropriate action, that is shift, reduce, or accept. And this all will be now discussed by my other team members.
My name is Sanjana. My roll number is AP 21110010313. So, as my friend explained about what is SLR parser, I will be continuing this and explaining it with an example. So, let us try to construct SLR parser table for this grammar. So first of all, before we construct the SLR parser table and the diagram, we first need to know the first and follow of all these variables. Here we have four variables or non-terminals, which are capital S, capital E, capital T, and capital F. So as we know how to calculate the first and follow, So first of S will be first of E, and the first of E is first of T, and the first of T is first of F, and first of F is first of F is ID. So as we know that first of any non-terminal symbol or a variable is always a terminal symbol, and here the only terminal symbol is ID. So as S depends on E, as the first of S is E, first of E is T, first of T is F, and first of F is ID. So basically the first of S will be ID. Similarly, first of E will be ID, first of T will be ID, and first of F will be ID. So here we have the first of all the four non-terminals or the variables is ID. Next, as we know that S is the terminal, as S is the start symbol, so the follow of S will be dollar. And since S does not appear on right hand side in any of the four productions, therefore the follow of S will only be dollar. Next, E. E appears on right hand side at two places. In the first rule, there is nothing on the right of E. So we will take the follow of S. So the follow of S is dollar. So we will have dollar in follow of E. And another place where E appears in the right hand side is in this rule, second production rule. And right hand side of E is a terminal symbol which is plus. So follow of E will be plus also. So in general, adding the two, it will be dollar and plus. And there is no other production rule which has E in the right hand side. Next, coming to T, T appears in the two productions here and here. So here, if we take this production rule, it is E plus T. So as there is nothing on the right hand side of T, so we'll take follow of E. The follow of E is dollar and plus. So we'll write that as it is. Here also there is nothing in right of T, so we'll take follow of E, which we already did. Next production where T appears on the right hand side is this third production. And the right hand side of T is terminal symbol star. So the follow of T will be star. So so adding all the three, the follow of T will be dollar, plus, and star. Next, the follow of F. For F appears on right hand side only in this production. So here, as there is nothing on the right hand side of F, we will take the follow of T from the follow rules. So the follow of T will be written as it is for the follow of F. So dollar, plus, and star. So this is the first and follow of all the four variables or the non-terminal symbols we have in the given grammar. Next, after this, the next step to construct the SLR parse table will be to write the augmented grammar. Augmented grammar is basically we introduce a new variable s dash, which is the new starting symbol, and we will have the production s dash tends to s dash tends to s. S is the initial start symbol of the production given to us. But now, since we are writing the augmented grammar, therefore the new start symbol will be s dash. After we create the augmented grammar, we write the LR0 items. Basically, LR0 items is for every production, we on the right hand side, we introduce a dot. So for s dash tends to s, we write a dot just after the in the beginning of right hand side. Similarly, for each production, we add dot symbol on the in the beginning of the right hand side. So this becomes our I0 state. So this is the I0 state of our grammar. Next, we have I1. So basically, as my friend told, that there are two functions, go to and action. So here, this is the I0 state as we know. Then from here, we get the I1 state. How is, since first, see the first production rule, s dash tends to dot s. So here what we do is go to I0 comma s. So I0 comma s, we apply the go to function. So that basically what it does is it shifts the dot to one step right. So now it becomes s dash tends to s dot. Similarly, that will be s1, that will be I1. Similarly, if we apply it for this, so I2 will be uh, go to of I0 comma E. So when we apply go to function with E on this production, it will shift the dot symbol one place to the right, so it will become S tends to E. And once it happens, it becomes S tends to E dot. Now we also need to see if there is any other production which has E on the right hand side. This is the production which has E on the right hand side, so we'll shift the dot in this production also to one position to the right. So this will become E tends to E dot plus T. So this will be E tends to E dot plus T, and S tends to E dot will be the two production. Now we'll apply the same rules to the next production. So next production is E tends to dot T. So here we'll shift the dot to one position right. So it will become E tends to T dot, E tends to T dot. And also we need to see if there is any other production rule in which T appears on the right hand side. So this is the production which has T on the right hand side. So in this production also, we'll shift the dot to one position right. So it will become T tends to T dot star F, T dot star F. So this is the I3 production. Next, T tends, now we need to see that for the next variable. So next variable is F. So T tends to dot F. So we will shift the dot to one position right. So it will become T tends to F dot. And there is no other production which has F on the right hand side. So this is the only thing. So that will become I4. Next, I5 will be for the next production. So we'll see this for, we'll do go to of this I0 for ID. So when we do apply that function, so dot shifts to right hand side. So it will become F tends to ID dot. So this is our. So now as we see that we got all the five productions, I1, I2, I3, I4, I5 from I0. If we observe all this carefully, we see that there are two states, I1 and I5, in which the dot is at the rightmost position on the right hand side. That is I1 and I5. So these are reduced states because the dot symbol is at the last position of the right hand side, and there is no other terminal or non-terminal symbol after that dot symbol. Therefore, I1 and I5 are the reduced states.
My name is Parsing and my registration number is AP21110010324. Now continuing, as we have already discussed here, this is our augmented grammar and this is the initial state which is I0 state. Now, I'll come to these slides. First, let us go into the transition diagram to understand how things exactly work. As you can see, here we have that same augmented grammar in I0 state that we already discussed earlier. Now moving forward, as we can see, the dot here is behind the non-terminal. Hence, we have to give the transition input as S and we transition to a next state, which is I1. As this is a non-terminal, hence we call it as go to I1 state. Similarly, as we can see our second, as we can see our second input here, we see that this and this input are taken together. As you can see, all belongs to E. Hence, and the dot is below E, behind E. Hence, taking this into consideration that dot is before non-terminal, we give input as E and we transition it to a new state I2. As we can see, the dot here shifted to the end, but for E, the dot shifted to right of E. Now it has a terminal symbol ahead of it. We'll come to it on the later part. Now let's move to the another state. Here we can see that we have T given to the input for E tends to dot T. As we give, it goes to the new state, I3 state, where E gives T dot. And accordingly, T gives T dot star F. As you can see, for the first grammar here, the dot is already on the rightmost side. That's not a problem. But the thing comes is for the second grammar, after dot, there is another terminal symbol. We'll come to it in the later part. Now let's move forward. As we take this grammar into consideration, we gave transition input as F and it transits to I4. We say go to F and it transits to I4. As we can see, the dot is on the rightmost part here. So this is also our one of the final states. And similarly for F dot ID, we gave transition input as IT, and here the shift occurs to I5 state, or we can say the fifth state, where we write F tends to ID dot. Now, moving forward, we see this as our final state, this as our final state, this as the final state, but here we have two grammars which are yet not final. So let's focus on them. Continuing the numbering of the transition states, we see here after dot we have a non-terminal plus. So we give plus as input and we shift to I6 state where we write E gives E plus dot T. As we can see here, T after dot we have again a non-terminal. So hence we have to write the same transition, same grammar for that non-terminal. Here we write for T we have two grammars. T tends to dot T in multiplied with F, then T tends to dot F. Taking this into account, we also see that there is another a non-terminal here after dot. Hence we have to write grammar for F as well. Now continuing, here we can see after dot we have again T. So giving input ST, we go to another state I8 where we get this after the non-terminal. But we can see that we also have to write for the transition state T tends to dot T multiplied with F, which is T dot into F. Now here we give star as input and we reach to the I7 state. And similarly for this state, after giving F as input, we reach directly to the end. And for this state as well. Here we can see we wrote these statement because these are already done. 17 we achieve here. 14, sorry, I4 we achieve here. I5 we achieve here. Now let's move for the I7 state, which is this state. As we can see, after dot we have F. So we write the transition state for F, but we see this is already achieved in I5. Hence, we give this to the I5, and this transition we get here. Now, if we go to these steps behind, this is the same thing that we already just written in terms of F. I6 we go to, then I6 becomes E, tends to E plus dot T, and all those T belong to. And when we go to our original.
So hi, this is Ayon Sarkar, and my ID is AP21110010286. And as we have come to the end of the presentation, so now we'll have a look at the SLR table. So primarily what SLR table is, SLR table consists of three primary things. First of all is state, then action and go to. States represent all the states that we have in our TFA presentation that we have can see here. And the next action table consists of all the transitions that will occur or the actions that will occur for the terminal symbols. And the go to table consists of all the actions and transitions for the non-terminal symbols. So for example, for the zero state and the ID, we can say it says S5. What does that primarily mean is and what R1 refers to is that we reduce using the first production rule. So the first in SR, S means for shift, the R means for reduce. And for example, you can see in the second, third states as well, it actually just gives like what action we need to perform on the particular stack. And in the go to table, we can see, for example, in the zero state, if under the go to portion of the table, what it essentially means is that, for example, if from the start zero, if you encounter S non-terminal symbol, so it will state that we should go to the first state. And for example, in the zeroth state with E non-terminal symbol, we should go to the second step. As similarly, we can say from the T, if you encounter T, we'll go to the third. If you encounter F, we'll go to the fourth. And the similar way, if in the sixth state, if you encounter T, we'll go to the eighth one. And if you encounter F, we'll go to the fourth state. So this is just a basic definition of the and a basic description of the SLR table. And now we'll go to the next slide. So this is just what you want to say is like an example of how actually SLR table works. In the previous 10 slides, we have encountered that what is SLR parser and how does the primary components of it and how it works. Now we'll go to an example. So by default, there will be 0 in the stack. And now this SLR input is getting ID in the first place. So as you can see from the table, if it encounters ID from state 0, so it mentions that to shift 5. So you're adding 5 in there along with ID. Now we can see that on the top of the stack there is 5. Identifier. And in the second step, we can see that um, now encounter with the fifth state, there is asterisk. So we can see that there is fifth step and asterisk, it is saying R6. So we should reduce using the sixth production rule. So we are reducing the identifier to F. Now we can see we're encountering fourth along with asterisk. So what should we And in the fourth one, we can say that along with 3 we're getting asterisk. So let's see that what's there for the 3 and asterisk. So it's saying that this our table, it's shift 7. So we are shifting just 7 into the stack. Now we're having at 7 and identifier. So for 7 identifier, we have shift 5. So we're shifting 5 as well as identifier into the stack. Now there it is 5 and plus. So we can see in the start table, there's 5 and plus, it corresponds to R6. So we are reducing using the 6 production rule. So after that, we are getting the in the stack 9 and plus. The 9 and plus, we can see it is stating R4. So what to do is that to reduce using the fourth production rule. And in the similar way, we have to fully reduce it. And in the end, if we get S1, that means that is accepted, and as well as we don't have any input remaining in the input string. So that will indicate that the string is fully accepted by the particular grammar. To wrap up our exploration, SLR parsing through simple is a powerful tool in compiler design. Its efficiency and practicality have made it a popular choice for many compilers, particularly for languages with relatively simple syntax. As you delve deeper into the world of compiler instruct construction, you will encounter a variety of parsing techniques, each with its strengths and limitations. Thank you.